How's it going? Hope you're all doing alright. Alright, you may have noticed I finally graded the tests. Most of you probably had a pretty good idea what your grade was, but it's nice to go through and finalize that. I went back and if you look at your test, you may have seen that I changed some of your grades. They were initially counted wrong because of the way that was entered, either with extra zeros or not enough zeros, or typed a comma instead of a period for a decimal, and things like that. I give you the points back. If you're off by like 1/1000th of a decimal, then I probably gave you the points back for that. There's a few other things I looked at too, just to try to get back points where I could. I do hope to go over that test at some point. And show how to properly work those. And I don't know when that opportunity is going to be. But anyway, do you all have any questions about section 7.2? Alright, we're going to look at section 8.1 today, and we'll see where we are with time after that. Before might try to start 8.2, but like I said, we'll see how it goes. Be nice if we get through chapter 9 before Thanksgiving. Anyway, we'll see. Because I still need to cover like a section or two out of chapter 10, unfortunately. Gosh, it's gonna be a little accelerated. No, I don't want to accelerate it. It's going to be a little tight for time, though. But we'll see how it goes. Alright. So in section 8.1, we talk about the distribution of the sample mean. And so the idea, let's look at a few definitions first. We have what's called a sampling distribution. And this is a probability distribution for all possible values of the statistic computed from a sample of size n. Okay, and the idea is that we have we have a population that we're working with, whatever that population happens to be, and we take a bunch of samples of size n, and some of the values may be in common, but maybe not between the different samples. But we calculate whichever statistic we're interested in. In this case, we're talking about the distribution of the sample mean. So we're talking about the x bar, the sample mean. So we calculate the x bar from each of these samples, and then each of the different x bar values form their own distribution. And it turns out that this distribution is approximately normal. Okay. And that's important because now we can use the same techniques that we looked at in chapter 7 to apply them to this material in chapter 8 now, which is using the calculator or looking up values on tables like we did. So the book goes on to say x bar is the probability distribution of all possible the sampling distribution of the sample mean x bar is the probability distribution of all possible values of this random variable x bar computed from a sample of size n from a population with mean mu and standard deviation sigma. Now it's important to keep in mind the different notation that we're going to be working with here. X bar is our sample mean. N is our sample size, which we've been using all along as sample size. Mu is our population mean. And sigma is our population standard deviation. So, in section 8.1, we looked at the distribution of the sample mean, x bar, and then 8.2, we look at the distribution of the sample population or sample standard deviation, which is S, which turns out to be entirely different what we have to do there. Of course. Anyway. And then after we get through 8.2, we'll jump into chapter 9. I think in chapter 9, we're only going to do through 9.2. I think I was supposed to cover 9.3, but I might abandon that just in the interest of time, which I don't really want to do, but there's stuff we still need to get to beyond that. So I'm kind of planning for the next couple of weeks, because we only have this week, part of next week, and then the week after Thanksgiving. So we absolutely need an opportunity to review for the final. I hope you all had a chance to fill out that survey for the final exam, because whatever ends up being decided, that's what all of us, whoever votes for what, that's what all of us as a group will do, because I don't want to kind of mix and match from there. So it's just whatever we all choose to do. So that's your choice, so be sure to make it. Not nearly as important as voting for president, but it does more directly, it does affect you in the near future. Anyway. Because, I don't know, we're like 4 weeks away from the final at this point. It's a little scary, but I think we'll get through it. So, anyway. So we have our sampling distribution for the population mean. Now, like I said, the idea is that we get all these different X-bar calculations from all these different samples of size n, and all of our different X-bar calculations form a normal distribution themselves. And so what that means is for a given sample size, it's more likely that the sample mean is going to be closer to the population mean than it is to be further away. The population mean is the population mean for a reason. And so the idea that we could take a sample of 25 people and end up with a sample mean very different from the population mean is very unusual. In fact, that's the example that I want to go over. I thought I had the problem written out here somewhere. Oh, yes, I do. What I wanted to do, and this is what I wrote in my last class. We know from our... I don't want to give away the answer, though. Let me utilize this. We know from our homework problem that is assigned from section 7.2 that human pregnancies are normally distributed with a mean of 266 days and a standard deviation of 16 days. So we want to find the probability that one random woman will have a pregnancy that lasts less than 260 days. And then 2, the probability for a group of 25 women that the mean lengths of their pregnancy will be less than 260 days. So the first one is essentially a 7.2 problem like we did in our homework. And the second one is a section 8.1 problem relevant to what we're looking at now. Now we do have a different z-score formula for sample distributions. This is a z-score for a distribution of the sample mean. And it says that z is equal to, there we go. Z is equal to x bar minus mu divided by sigma over the square root of n. So notice instead of a single data value x, we use the sample mean x bar minus mu, and then the standard deviation, when there's a sample size of size n, in this case 25 that we'll look at, that means the sample deviation is then modified. This is the modification of the sample deviation for a group of size n. So really the standard deviation gets smaller the larger the sample we have, which is significant. It does affect this significantly. Now, it's not very useful in this form. Instead, I think it's a little bit easier to write square root of n times x bar minus mu divided by sigma. That ends up being, from a calculation standpoint, a little bit easier to handle, I think. So you can use either formula, but this one will probably be easier to work with in terms of putting numbers into a calculator. So I encourage you to use this format. This format kind of tells you, okay, the standard deviation is being modified by this value, so it's actually smaller for a sampling distribution. But this is more of a computational formula, is what I would call it. Makes it easier to calculate the value. Anyway, so that's our z-score for a distribution of the sample mean. So let's look at problem 1 there, which, let me bring that back down. The probability that one random woman will have a pregnancy that lasts less than 260 days. Okay. So we know mu is 266, sigma is 16. Now we're given a data value of this time of x equals 260, and we want less than specifically. That will tell us where to shade. So we're only looking at one individual, so this is just one data value rather than a group of data values. So that's why we know to use this formula, z equals x minus mu over sigma. This is the formula for z that we use when we only have a single data value. If we have a sample of size n, then we want to use this other formula. And that's how we can tell the difference immediately. Whether we have a sample of 1 or a sample of size n, then we use these accordingly. Okay. So we know that we have 260 for x minus 266 divided by 16. Negative 6 over 16. It's negative 3/8, so negative 0.38. It's 375, but we're not round to 3/8. Anyway, so we look at our graph. We know 0's in the middle, so negative 0.38 is a little bit to the left. And we want the probability that it's less than 260, as we said in the question. So we shade the area to the left. Okay. Now, we want to find our area or our probability. So our lower bound, goes to the left, so our lower will be negative 10, and our upper bound, or upper boundary, or right edge, would be, this is negative 0.38. And so we can use the calculator from there. Go to second data, over to distribution, normal CDF, and Go to lower and upper. We have negative 10 as our lower, and negative 0.38 is our upper. Calculate. And we get a value of 0.35. Let's see, that'll round to 0.3520. We have a 197, so that 7 rounds to 19 up to a 20. Okay. It's a pretty good probability that a randomly selected woman will have a pregnancy that lasts less than 260 days. About 35% of the time that happens. I don't know if this probably includes premature births, but yeah. Anyway, usually when you think about pregnancies, we don't have that massive tail to the right, so we know that premature births are an issue and a huge problem, and but sometimes that's the only way to save the child. But you never hear about someone carrying a baby longer than like 10 months or 11 months. That would be crazy. Especially, that would not be a happy woman at that point, I imagine. So, anyway. Because you hear about 7 months premature, be premature at 7 months, but you don't hear about the other end, like 11. At some point, I think they just do a C-section and call it a day, or induce, or etc. Anyway. So I don't know how accurate this is on the higher end of the spectrum. At least on the lower end, we can be fairly accurate. Anyway, this doesn't really affect the outcome of the problem. I just find it curious. Anyway, but nothing I've really studied in my life, so I can't say. Part 2. Probability for a group of 25 women that the mean lengths of their pregnancies will be less than 260 days. It's really the same question, but instead of looking at one random woman, we're looking at a group of 25 random women, basically. And this is because we have a group of 25, we are going to use our different z-score formula. We still have the same mean, standard deviation for the population, but now we want x bar to be 260 or less, and n is 25. So we have a little bit more data available in this case. There we go. Good. Alright, the reason we call this x bar instead of x is because we know this is the sample mean for this group of individuals, a group of women. And so, because we're talking about a group of individuals, we're going to use x bar instead of x. X is reserved for a single data value. X bar is reserved for a mean for a multiple data values, or a sample or statistic for multiple data values, I guess I should say. So our z-score formula that we'll use, let's use square root of n times x bar minus mu divided by sigma. Okay. I use 25 because it's a perfect square. It's a nice number to work with. The book, the problems out of the textbook are not as kind, unfortunately, so we'll have to bear with that. Let's see, and then mu is 16, or sigma is 16. So what we have is we have a 5 is the square root of 25, and if you're not comfortable with that, again, most of the ones in the book you'll have to do on the calculator anyway, because they're not perfect squares. But feel free to put that into your calculator. Square root of 25 is 5. So we get 5, and then negative 6 for our subtraction here, and then 16 on the bottom. So z is negative 30 over 16, multiplying those two together. And we approximate that. So let's see, Negative 30 divided by 16 equals, that's not equals, I pushed the wrong button. Okay, negative 1.875, so we'll call it negative 1.88. Okay. So that's our z-score. Notice it's a much smaller z-score than we got in part 1, negative 0.38. Okay. So we go ahead and make our graph. And we know we're shading to the left because we said the mean for the group was 260 days or less. And so our lower is still negative 10, and our upper bound is negative 1.88. So now we're going to put that into the calculator. Distribution, CDF, enter, so negative 10, negative 1.88. Calculate. And our probability here is 0.03. Looks like it rounds to 0.01. So this is slightly more than 3% chance. Now we think about that, and in comparison to the previous question, we want to look at these two things together. This is a chance a single individual woman, I don't want to say single, that's kind of a loaded term. So one individual woman, a little over 35% chance that the pregnancy lasts less than 260 days. But for a group of 25 women, the chance that their mean length of pregnancy lasts less than 260 days is only 3%, which, statistically we call that unusual if it's less than 5%. So it's an unusual outcome for a group of 25 women that their mean length of pregnancy would be less than 260 days. Again, the reason is, and we mentioned this a little bit before, is because when your sample size gets larger, then the likelihood of you being further away from the mean gets smaller. So when you increase your sample size, the chances of being different from the population mean decrease. And so we see that this is only a difference of 6 days from the mean, but we see it's a very slim chance of this occurring. So what we're saying is it's basically 94% chance that the length of pregnancy would be between like 260 and 272 days for that group of the mean length of pregnancy for that group of 25 women. So again, what this ultimately tells us is that once we get a group of individuals and take the sample of that data, then this likelihood of being this far away from the mean, and again, it is relative to the standard deviation and the sample size. Those are all factors in this outcome. The likelihood of it being less than 260 in this case is very small, 3%. What is more? So what we think is happening here? Well, when we have a group of individuals, I mean, they're going to have all kinds of different pregnancies, more than likely. One of them might have a length of pregnancy that's 250 days, which is shorter than usual, but not out of the question. Another one might have 255. Another one might have 262. Another one might have 270. Another one might be 267, 266, right on target, 272, and we can keep going from there. they're going to be kind of all over the place, but collectively, the mean of those values are expected to be pretty close to the population mean of 266. Even with a relatively small sample size of 25, it will very likely end up being pretty close to that population mean. And the larger our sample size grows, the more likely it's going to be right on track with that population mean. Okay? So if we increase the sample size from 25 to, say, 100, this number will drop even more. It'll be even less likely to be 260 or less. Because what would happen in there is that ultimately we end up with a group of outliers that we just found that for this research, where all of them have shorter than normal pregnancies. That's about the only way that we can have this happen. For to have a mean of 260 or less in this group of 25 individuals is that, at least some or a good number of them are outliers, so that we end up with a smaller than usual mean. And so that's what the section is talking about. Is we're talking about a group of individuals. The probability of being close to the mean is high, while the probability of being further away from the population mean is low, as we can see here. And this leads us to our central limit theorem, which is a very significant theorem in statistics. Let us start a new page. And I've kind of paraphrased this already. Regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as sample size n increases. There's an L in there. There we go. Regardless, I'm trying to read this from the textbook, but it kind of got a glare from the light at the worst possible angle. Regardless of the shape of the underlying distribution, or the underlying population, I'm basically saying that the population can be whatever. There doesn't have to be rhyme or reason to the population. Like normally we hope it's approximately normal shaped. It's not really the case here. But what we're saying is that the distribution of the sample mean will still be approximately normal as the sample size increases. Okay. So there's our central limit theorem. Alright, and that turned out to be a significant result, because we may not be able to make claims about the individuals in the population, but we can certainly find out a lot about them through their sampling distribution of both the mean and the standard deviation, as we'll look at in section 8.2. Okay. Now, beyond that, there's really nothing different in this section. When you look at the applications here, the problems are all essentially the same. It's just a question of calculating our z-score using the new formula, of course, and then plotting it on a graph, and then going from there and calculating the probability, whether it's to the left or to the right or between. It's really the same type of problems that we were looking at in section 7.2, but now using this other z-score formula. It's really not terribly different in that sense. I want to look at number 22. And this is on page 405. Oops. There we go. Sort of. I'll do that. Alright. This is about Old Faithful. The most famous geyser in the world, Old Faithful in Yellowstone National Park, has a mean time between eruptions of 85 minutes. If the interval of time between eruptions is normally distributed with a standard deviation 21.25 minutes, answer the following questions. Okay. So this geyser erupts every 85 minutes on average, although there's some variation there because it could be as using a standard deviation of 21.25 minutes. Reasonably, we could expect it to be as short as 40 minutes and up to 120 minutes between eruptions, which is quite a big differential, to be honest. But the highest likelihood is being between those two numbers. It could actually be shorter or longer than that, but very unlikely. More than 2 standard deviations is unlikely, so if we subtract 42.5 and add 42.5, we kind of get the extreme values that we could expect. So I would say 40 minutes to maybe 130 minutes would be the extreme we would see, based on these numbers that they've given us. But more than likely, it'd be pretty close to 85 minutes. That's for just a single eruption. So, what is the probability that a randomly selected time interval between eruptions is longer than 95 minutes? Now again, we have to pay attention to the wording. Notice they did not give us a sample size in this question. They said, what is the probability a randomly selected time intervals, this is just one interval of time between eruptions, normally is longer than 95 minutes. So we'll use the z score formula, z equals x minus mu over sigma. Because we're not given a sample size, we're looking at a single value, we'll use the simpler formula. Okay, this is our x, 95. So we subtract, we get 10 over 21.25. And we divide that. And I get 0.47. Okay. So is it longer than 95 minutes? So in our graph, we'll find 0.47. shaded to the right because so you said longer than. So our lower is 0.47. Our upper, we'll use 10 in this case. So 0.47, 10, calculate. So the probability here is 0.3132, or no, sorry, 3192. I read that wrong. Okay. So almost 32% chance that a single eruption will last longer than 95 minutes. Now for part B, what is the probability that a random sample of 20 time intervals between eruptions has a mean longer than 95 minutes? So now they give us a sample size of 20, and we want the probability that the mean is longer than 95 minutes. Okay. So when we see that, it tells us we're going to use the other z-score formula. We'll use square root of n times x bar minus divided by sigma, and then this is x bar now instead of x. N is 20. It's not a perfect square, but we can work with it. Okay. What I would say is on your calculator, first thing, I would go ahead and subtract these two numbers because generally that'll be pretty straightforward. But because we don't know the exact value of the square root of 20, there we go, and because it is actually an approximated value, I would say let's go ahead and do square root of 20 on our calculator. Now, notice on this calculator, at least, when I press the square root, it opens up a parentheses. And I think the graphing calculators do the same. So let's make sure we close that before we do anything else. And then we'll do times 10, and then divided by 21.25. We can do that all in one operation here, or one series of operations, as we see it here. So we have square root of 20 times 10, and divide by 21.25, and we get 2.1, we'll call it 2.10 after we round. Okay. Make sure you're able to get that number on your calculator because it's useful to be able to do all of this in one kind of entry, one line entry. Not to do square root of 20 separately and then multiply by 10 and then divide by 21.25. Although you can do that. It's one way to proceed. I think it's nicer, a little bit easier to draw at once. So we got 2.10 for our z. And we wanted it to be longer than 95 minutes, so we'll shade to the right once we graph that. 2.10 is a little bit further right than usual, but we want the area to the right of it, so we'll look at that. Our lower boundary is 2.10, and because it continues to the right, we'll call upper as 10. 2.10, 10, and calculate. So it gives us 0.0179 after we round. So that's actually a much smaller probability than we got for a single random value, which was 0.3192 before, about 32%. And this is less than 2% for a group of 20 different time intervals between eruptions. Very unlikely that for 20 eruptions that the average would be over 95 minutes. Excuse me. So we get to now C just repeats the same problem but with 30 instead of 20 as the sample size, and I can just go ahead and tell you now that that's going to decrease the probability even further if we increase the sample size. That's precisely what the central limit theorem told us. So now we've increased the sample size, so to be this far away from the mean is now even less likely. But if we go through and calculate it, we'll see exactly how much less likely. Probability that the x bar less than, or sorry, more than, we can say more than 95. With n equals 30 in this case. So our z is square root of 30 times 95 minus 85 over 21.25. Again, in our calculator, we'll just do square root of 30 times the 10 in the numerator, and then divided by 21.25 in the denominator. For that, we get 2.58 approximately. Again, notice we're rounding to 2 decimal places here, 2.58. Alright, so 2.58 is over here, maybe even further, but we're shading to the right. So our lower is 2.58, our upper, we'll go ahead and use 10. Put that all into the calculator. And for that we get a value of 0.0049. Yeah. So now it's less than half of a percentage point. It went from being a little less than 2% to be less than half of a percent. So even less likely, now that we increased the sample size to 30, but kept the number the same. And this is what we expected to happen. Excuse me. Now, this is what we expected to happen with the central limit theorem. By increasing the sample size to be this far away from the mean is even less likely than it was before. So D basically asks us that question: what effect does increasing the sample size have on the probability? Well, we've seen it directly. Going from sample size 20 to 30 causes a decrease in the probability. What might you conclude if a random sample of 30 time intervals between eruptions has a mean? That's a silly question. Sorry. Anyway. I don't know what they're asking there, so I'm not going to worry about it. Let's just skip B. F, on a certain day there are 22 time intervals for Old Faithful. Treating these 22 eruptions as a random sample, the likelihood for the mean length of time between eruptions exceeds blank minutes is 0.20. It was kind of reverse engineering the problem right there. Basically, what is the 80th percentile? Because what we're saying, anyway, this is part E. So what we're saying is that we want to find the value where the area to the right is 0.20. Okay, and we want to find the x value where that's true. Now, that means that the area to the left, does anyone know what the area to the left would be in that scenario? If the area to the right is 0.20? I haven't asked a lot of questions today. I've just been lecturing, so I apologize for that. I think the reason I'm skipping a lot of questions is because we covered a lot of this on the last section, so it's kind of repetitive in that sense, but not really, because we're using this different z-score formula. Anyway, if the area to the right is 0.20, that means the area to the left is 0.80, because it has to add up to 1. We know that the area under this curve is 100%. So if this is 20% of the area, then this must be 80% of the area, because together they combine to give us 100%. Now the area left is 80%, so basically we're looking at the 80th percentile. Doesn't matter which side we're looking at, we just want the value that represents the 80th percentile. And we looked at these at the end of the section 7.2 using the inverse normal function. Mu is 85, we already established that. Now, for our standard deviation, we'll use sigma divided by the square root of n. This is where we have to be careful in this problem, is we remember our original formula that we said for the z-score, right here. The original formula says that the standard deviation on the bottom is actually sigma divided by the square root of the sample size. These together represent the standard deviation for a distribution of the sample mean specifically. So these two are kind of taken together. That's why when we write it like this, I know some people don't like it when we rewrite it like this, but this is easier for computational purposes. This is really what's happening. This is our standard deviation right here. So we want to make sure we use that right here when we use our inverse normal function on the calculator. So that would be 21.25. And let me go back to the questioning because I forgot the sample size. 22 is our sample size. 22 time intervals, so we'll do square root of 22 on the bottom. Okay. So 21, turn the calculator on first. 21.25 divided by the square root of 22. So it gives us, let's call it 4.53 as the standard deviation. So now you go second data over to distributions. We'll go to inverse normal. Area is 0.8. Our mean is 85. And our sigma we'll use 4.53. Calculate. So 88.8 minutes. Okay. That's the thing that we have to remember about these problems where we have a sample of size n, is that the standard deviation calculation is actually sigma divided by the square root of n. That's why we have the different z-score formula. It's because of the standard deviation being different specifically. Because what we find is that for a larger sample, the smaller the deviation is going to be from that mean, which is significant as far as the calculation goes. So I don't know if you have to do this. I think you have to do it on your homework on one question. Oh, yes. So you use second data over to distributions, and instead of choosing normal CDF like we've been using all along so far, anytime we're working backwards to get like the original data values or some data value that makes a how to say this best. We're trying to find a data value that meets a certain requirement, like a certain percentile. Then we use the inverse normal operations instead. Now there's three values that we have here: the area, and then the mean, mu, and then the sigma, the standard deviation. Now the mu we already know is 85. That was given to us. The standard deviation we have to calculate ourselves. And as for the area, we said we're finding the 80th percentile, so I put 0.8 in. But again, the reason we chose 0.8, or we decided that's what we should put in, is we said here the area to the right is 0.20, and we want the area that means the area to the left is 0.80, and so that means we want the 80th percentile. The other way we think of this is that if it's 100% area down here, and we take away the top 20, then we're at the 80th percentile in that regard also. Okay. We want the value that delineates the mark between the lower 80% and the upper 20%, and that would be 88.8 minutes, as we found. Okay. Any questions there? On the 84 calculator, remember you have to go to second in distributions and go down to inverse normal there, and then it prompts you for everything. The 83s are a little bit different because we have to enter them in a specific order. So if you have the 83, like this one, we go second. No, we don't go second. Yes, we go second vars. We go down to inverse normal. Enter. Then we enter 0.8 for 80th percentile, comma 85 for the mean, comma 4.53 for the adjusted standard deviation, and it'll give us. Boy, I missed a number in there. Let me try that again. I'm sorry. I mistyped one of the numbers and it didn't give us a good answer. somehow I entered a 5 instead of 85, and that made a big difference, as it turns out. There we go. But yeah, we do get the same value either way. It just takes a little more insight if you have the 83, and I believe I included that on the formula sheet, so you don't have to worry about memorizing it necessarily. Anyway, any questions there? I've mainly been doing the calculations on the 36, one because they're easier, but two, I think it's closer to what most people have. But if you do have questions on the 83, just let me know, and I'll show you how to do an 83 for a particular problem. Anyway. I'm still trying to figure out what to do for the remainder of this semester here. So I want to have a third test. I think it's important that we have a third test. I still have to grade it, which is not great. Anyway. Thanksgiving kind of screws up, but basically it leaves us 1 day short of what I really would like to have. It's be 2 days short when it comes down to it, I think. What I might do, and I don't want to have to ask you this, but I might just have y'all watch an additional lecture between Wednesday and Monday on section 9.2. And it's not what I wanted to do, but that might be the only way we can get through everything. Yeah. That might be the only way. So I apologize in advance for giving you an extra lecture to watch. And not being there to interact. If we can just have, if it's just 1 extra hour, and if you want, you could come to my Thursday class this week and watch it live. That'll be at 9:30 Thursday. But otherwise, I'll just post the recording in Canvas. So I think that's the only way we can get to where we need to be. Unfortunately, we're 1 day behind the Tuesday-Thursday class, so they're going to make it okay. And if we were able to have class on Wednesday next week, we could, but I'm not going to ask you to go to class after noon on a Wednesday before Thanksgiving. That's not cool, even if we are all quarantined. That's not fair. That's our time. So. Anyway, I'm glad you are okay with that, Jacob. I hope everyone else is. So I will. I'll probably post about that Wednesday in case some of you want to try to make it to that 9:30 lecture. I don't know what your schedules are like, and I certainly wouldn't require you to do that. But otherwise, the lecture will be available on Twitch afterwards. So. Yeah, I think that'll be the best way for us to get through everything, and I regret asking y'all to do that, but and it's a problem of my own creation, but I mean we'll be okay otherwise. Anyway, at some point, we're going to have a third part of this project. I don't even know if I can ask you to do that at this point. I might just do the first two. We're at that point in the semester where you have to pare something down, unfortunately. So, anyway, it would have been great if we could have had this class in the classroom and just like had a normal semester and things wouldn't be crazy at the end. And I stay on track a little bit better in the classroom, believe it or not. I get a little distracted when I'm here, just talking to a webcam. So, all right, so we'll stop there. I don't think we can accomplish anything in these next 10 minutes that will be helpful or encouraging to the next lecture. I think we'll just make it a standalone lecture next time. So we'll leave it at that. Y'all take care. Have a good rest of the day, and I'll talk to you Wednesday. Bye.